So I won't give my whole background, but I'm very much semiconductor person rather than from the blockchain Web3 community. I thought I'd open just an observation that has struck me since we've been working on this, is that they're really quite different cultures here. In chips, uh, it's super expensive to develop a chip. Rather than thinking in terms of cost to acquire a customer, we think of the NRE, the tool. It's basically like a manufacturing business. You have to think of the tooling. So gross margin is your key metric. You try to design a single chip for multiple purposes. And it's a big project. To do one chip is a huge deal. So we do not kick off chips with the same fluidity that you all kick off a new GitHub repository. It's just different way of thinking. The main point here is to say, I just want to emphasize, you can't be too insular in the thinking here, that you're essentially crypto wallets, crypto anything is using semiconductors that are largely designed not for you. They're designed for other purposes. You look at a typical MCU in a wallet, you probably have 100 such MCUs in your house. They were designed for those 100 purposes, not for crypto. So you have to be aware of the larger world and why these semiconductors came into being. And I think to harmonize requirements, that's how good semiconductor support comes into being. CrossBar is foundationally memory technology company, so I have to do an aside on memory technology. I think it's very relevant here in talking about crypto wallets. I'll explain why. But just to give some background, some of you may or may not know this. Any kind of non-volatile memory that you're used to dealing with, your SD card, your USB thumb drive, these are based on floating gate, meaning a bunch of electrons are trapped in a an oxide between insulators. This works down to, you can integrate this with logic. It works down to about 40 nanometer. Below that, the volume, you need a certain volume of electrons to be readable, and the volume is just too small, so it doesn't work anymore. So this has led broadly to a field called emerging memories. Means, what are we going to do for advanced nodes so that we can embed non-volatile memories? And CrossBar is a leader in one type of that memory, called it resistive memory. So to explain the relevance in cryptography, crypto wallets, so on, flash trapped charge, I summarize in this table up here, can be easily, it's a charge. You can read it with an electron microscope. Also, because it's a bunch of electrons trapped in a small space, they want to get away from each other, and they do leak over time. You may have noticed if you put something in your desk drawer and pick it up a couple of years later, maybe it doesn't work, particularly if you happen to throw something magnetic in that same drawer. So it's susceptible to radiation, magnetic fields, aging, not very permanent. And then, as I mentioned, can't be integrated with advanced logic. So a lot of what you see in a crypto wallet might be a 40 nanometer chip with logic and floating gate memory. Whereas resistive memory, highly immune to physical attack. We've given our memory to a teardown house, even with very expensive attacks like delaminating layer by layer, unable to extract the data from the memory. Also, it's does not have this repulsive leaking effect. We say it lasts 150 years. That's obviously based on analysis. We have not done a 150-year test, but much more stable in environmentally robust and radiation magnetic field aging. And then, of course, the reason for existence of emerging memories can be integrated with advanced logic. So let's jump to as we come looking at this field, obviously embedded memory, you think of security application because the logic and the memory can be together. So this is how we started approaching security products in general. Looking at crypto wallets, you could say most are pretty close to this kind of architecture, where there's a microcontroller kind of borrowed from consumer market, not shielded. I'll explain what I mean by that. Generally 40 nanometer or above, because it has to include the memory, and the memory stops working at these advanced nodes. And then perhaps a secure element really borrowed from the banking card SIM market. This does have the kind of shielding I'll explain a little bit later. But some are simple state machines, some have a small MCU, a few pins. Typically, they would support, of course, RSA of P256. So, kind of legacy inapplicable crypto when you're talking about crypto wallet. And then it's kind of hard to go beyond a black box view. You don't get like open dev kit like you would get for a consumer MCU. So the problems with that, a lot of wallets will, if they have an SE at all, they might pull the raw secrets over here and process them in a physically not shielded chip. That seems like a problem. Also, just the fact that you're making important decisions like, am I paying to the right address? That's UI software executing over here in an unshielded chip. Obviously, the exposed bus, you can say that's not a horrible problem because it's encrypted, but if you can capture it and crack it offline with arbitrary compute power, that's a little different than having to crack it in situ. Mentioned the speed and the size are large, and of course the memory is perishable and readable. And then I hear a lot of complaint about no dev kit access, almost black box or very little flexibility. So this coloring here is meant to be physical countermeasure shields. So let me take an aside to explain what I mean by that. It isn't obvious when you read data sheets of these parts, but if you look at teardowns, you come to a realization that a few small chips for banking SIM, they have physical protection. Whereas over on the MCU side, any MCU, general purpose MCU, even if it says secure, that generally refers to kind of logical security. By that, I mean, when I write this address, now I can no longer do this. There's some logic there. But of course, that logic is just transistors performing logic. If you can disrupt their operation, then that logical security malfunctions, does not work. So physical security means attempting to prevent that kind of attack. I'm not going to go through this slide. There's 20 or so different techniques that have to be distributed throughout the layout. I'll just quote one that's easily understandable. If you put on the top metal layer a kind of complicated mesh that maybe has 64 or 128 lines all spaghettied around each other and then connected to sensors, if you try to fib or probe, you're going to either short or break one of these. Then this is called a protective active mesh. That's just one of about 20 techniques. The point is they have to be built into the chip, distributed throughout the layout. What you find in the marketplace is you only see that kind of physical protection on these SE chips. You do not see it on a general purpose microcontroller. Also point out that when you talk about fibbing, probing, 28 nanometer by itself is of course more resistant to attack than 40 nanometer and so on. But also the effectiveness of these countermeasures is much higher. That mesh is much more dense when you have it at a more advanced process. So last slide, I'll just say some of the things that we think about as architectural improvements. And we have some plans in this area, but I'll just talk very generally here about how to improve these. These are kind of things we can discuss today. Of course, being a memory technology developer, we first talk about let's replace all the, whether it's secret storage or the boot code or backup that you would typically do on an SD card. Replace that with a private and persistent memory that's robust. Also, I think extending physical countermeasures over more function. There are very important functions going on typically on this MCU side, whether that's 2 chips or co-package or monolithic, however you do it. Extending that umbrella of physical countermeasures seems like key for a number of reasons. One is, as I mentioned, there's critical decisions going on over here, but also you could say crypto is evolving really quickly. And I don't think you're ever going to have purely hardware implementation that keeps up with the rate of innovation in blockchain. To the extent that this is a secure microcontroller of some power, you can think of it as a secure enclave for processing even the cryptographic functions. And then, moving forward in Node is good for cost, power, size, everything. And of course, supporting user with a complete dev kit for all of this, so you don't have a black box over here that's hard to use. So these are some of the techniques that we think are important in semiconductors in products going forward. I think I'll stop there.
Thank you.